and I will invite the first speaker to come up, which is Ric Davies from MPE. And Ric's very kindly accepted an invitation to speak and give us a summary of where he sees some options for high-resolution imaging in the next little while. Ric, thanks very much.
Thank you very much. I'm not going to talk about everything to do with high-resolution imaging. I'm going to limit myself to talking about adaptive optics and interferometry. And in particular, I want to say a little bit about where we are and what we can look forward to in the next 10 years or so. And I want to illustrate this with some different science cases. I've chosen these four up here, not just because I think they're interesting, but because it's very convenient for me, because they're the science cases we've been looking into more detail in the instrumentation projects I'm involved in. So I want to start by just giving you a very brief history of adaptive optics. And in fact, there's only two important milestones in adaptive optics. There was 30 years ago, the very first astronomical image correction on a 1.5 meter telescope, and that was very exciting. And about 10 years ago now, a very, very high order correction on the LBT, on the 8.4 meter telescope there, which was effectively the first extreme adaptive optics correction. And it's also important because it's the first telescope that was built with adaptive optics built into the telescope itself, so with an adaptive secondary mirror. And you can see some very impressive airy rings around the point source here. There's a couple of other points I'd mention here. Very high resolution measurements, 22 milliarc seconds measured on the Keck telescope, and 35 milliarc seconds achieved with image selection, both optical wavelengths if you need to get to the very highest resolutions. What we can look forward to is somewhere in the middle of the 2020s is the ELT coming online and giving us another step forward in terms of spatial resolution. So here we are now. My history actually didn't include anything about ESO, but we're an ESO member state here, and so we should say something about ESO, and also because ESO has actually done a lot of fantastic work with adaptive optics and fantastic developments. What we have is the VLT, where in the near-infrared you can reach 40 to 60 milliarc seconds, and the VLT has been around for 20 years or so now. And we also have the VLT interferometer, which can get you down to just a few milliarc seconds. And if you've got an interferometer with multiple telescopes, you can have lots of opportunities for first light. And I wasn't sure which one to put down here. So there was first fringes with the 8-meter telescopes, 2001. But with 4 8-meter telescopes, it was only just a couple of years ago. And this has opened up a very exciting new range of astrophysics that we can do. Right at the moment, there's a new telescope being built, the ELT, which will have first lights around the end of 2025. And this will give us about a factor 5 better resolution. So in the near-infrared, you can expect something around 10 milliarc seconds. So this is quite different to what we can achieve now. It's very hard to imagine the difference in size between the VLT and the ELT. So this is just a photo of Roberto Tomai explaining ESO's plans to put the VLT on the ELT Naismith platform. just so you can really appreciate the size difference. And I thought, because what we build on the ground, we have to have the context of what's in space as well. I thought I should put JWST on here as well. We think of that as a big telescope. It's a big telescope for space, but it's not a big telescope compared to the ground. We can get higher resolution now on the ground than JWST will achieve. That's about the right size compared to these two telescopes. So these are the sort of telescopes I'll be referring to in the science cases during my talk. I don't normally go in for predicting the future, but I was talking to Eric Höger about 5 years ago, and he was planning a successor to the Gaia mission. And I said some things to him that I didn't realize he would actually quote me in his document. And you can look it up on ADS, on the abstract server, if you like. And basically, this is in the mid-20s, we're going to have the first adaptive optics on the ELT. I think that's a fairly secure thing to say. Maybe not 2024, but not too soon afterwards. I think it's going to be around 2030 before we get wide-field adaptive optics on the ELT. And by wide-field, I mean correcting actually a whole arc-minute field of view. Around that same time, I think that's about when we're going to get visible AO on the VLT. And by visible AO, I don't mean high-contrast imaging on single sources. I mean high-contrast. I mean adaptive optics with a bigger sky coverage with wider applications and just high-contrast imaging. I think it's going to be 2030s as well. And if you think very far in the future, I expect it's going to be something like 2050 before we get visible adaptive optics on the ELT. So this I would, in the 5 years since I said this, I don't think my expectations have changed. We'll see how they change in the next 5 or 10 years. So I want to also say something about interferometry, because interferometry is a fantastic way to get very high resolution imaging. And I'm just showing 2 examples here, one from the Cara array with a Mirk instrument, And this was published a couple of years ago. And it shows an image of a star. This star's not flattened, it's just the projection is put out to show the whole surface of the star. And this imaging showed that it was a direct view, basically, of the huge sunspots or star spots on this star, where the temperature is much cooler. There's a lot of very strong magnetic fields over a large part of the surface, and this is affecting the cooling and the structure of the star surface. And you can get these fantastic images with interferometers. Here's another one with the VLTI. I don't even know how to pronounce this name, Pi1 Grus or something. It's also showing structure on the surface of a star. This is a huge star, and these structures are much bigger than the sun. But it's basically telling you about the granularity, so again, about the convection flows in the stellar surface. And basically in this star, there's no models for stars that are this evolved and this large, but it's basically if you extrapolate from the models that do exist, then the measurements here agree pretty much with that. But the point here is to say that interferometry at the moment is largely stellar interferometry, looking at stars because they're bright objects. And you need bright objects to do interferometry because for every telescope you add, you have to split the light in real time up into more and more components, and you basically lose photons very, very fast. There's a game changer, though, I think, and it's called gravity, and this has allowed you to do quite a lot of interferometry, or will allow us to do quite a lot of interferometry on extragalactic objects. And I've just shown a couple of images here we've obtained with gravity, which is basically imaging the dust sublimation radius region around active galactic nuclei. So this is a region just a few tenths of a parsec from the active nucleus. I'll start on the right. This is an image. We've got much better resolution here, but I'm not allowed to show it yet. So this is an image of the dust sublimation radius in NGC 1068, and you can see there's actually structures resolved here. This is just a few tenths of a parsec, and it's absolutely remarkable, particularly that the orientation of this structure is very much the same as the orientation seen on larger scales in the mid-infrared with interferometry, and also with the maser disk, and also with the radio continuum. And we can learn about the geometry of the structures around active galaxies from these images. Here's another one in another AGN. This is NGC 3783, and you can see this is also elongated, but there's another structure coming out here. And these colored points on here are in fact from velocity measurements of the broadline region, which we can also spatially resolve in this way. So you can see there's a velocity gradient in the broadline region along the same direction as the dust, the hottest dust is elongated. So whether this is rotation in the broadline region and the dust is in the plane of the disk, or whether it's tracing an outflow and the dust is in the outflow, we have yet to decide because it's a bit of a complicated object. But you can see already that with interferometry, you'll now be able to resolve the central fractions of a milliarc second almost of these galaxies. So that's enough on interferometry for now. I want to turn to what we can do with adaptive optics and talk about some science cases we can do with this. And this is basically where we are on the VLT at the moment. In seeing limited scales, we've basically taken large samples of galaxies at high redshift, hundreds, maybe thousands of galaxies, and we know basically what their global properties are, and we have some idea of their structures and their sizes and so on. But what we also know is that to really understand galaxy evolution, we have to spatially resolve what's going on in these galaxies rather than just the global properties of the galaxies. So we need to look at the inflow in the disks of the galaxies. We need to look at the bulges and how the bulges are forming. We need to look at the star-forming clumps and resolve the galaxies into these clumps. And we need to understand where feedback and quenching are occurring. And if you look at the resolution you can achieve with adaptive optics on the VLT, here's one example galaxy with this BX610 it's called. This bar is 1 arc second, and you can see the PSF here. These are images obtained with adaptive optics from the ground, and these are images from HST, and you can see we're actually achieving similar resolution here. You can see velocity gradients, you can see different star-forming regions, and you can compare to the stellar light and the masses and so on, and you can even look at excitation diagrams. So there's a lot we're seeing, but it's on scales of a few hundred parsecs. In the near future, we're going to have JWST, and already we've got ALMA, so we can see much more than this. So this is just a comparison, not just of JWST, but of JWST and the ELT here. These are local galaxies, and if you were to redshift these galaxies to redshift 1 or 2, this is what they would look like. When you go to such high redshifts, galaxies actually look different, but this is just to illustrate the point. So JWST will be able to resolve these galaxies and see some of the structure. With the ELT, you'll be able to see the detailed structures in them, and this is really important to actually resolve all these components that I mentioned in the last slide. And so using these telescopes together to do high-resolution imaging is what we need. And with JWST, we'll measure large samples of objects, and we'll be able to select the samples, get the basic galaxy properties, but it's going to be at resolutions of half a kiloparsec to a kiloparsec. And bear in mind that at redshifts greater than about 1, an arc second is 8 kiloparsecs. And while we think of JWST as a high-resolution telescope, because it's working at longer wavelengths, the resolution will actually go from about 50 milliarc seconds at the shortest end down to about 0.3 or even 0.4 arc seconds at the long wavelength end. So the resolution we're going to get is not going to be much better than what we have right now, but the sensitivity will be much better. On the ELT, we'll have Mikado, which is my instrument, where we're going to be doing imaging, and we'll be able to trace these structures on scales of about 100 parsecs. Harmony is an integral field spectrometer for the ELT, and you'll be able to measure the kinematics of the emission lines and so on. And with ALMA, we can trace the molecular gas component. And by putting all these together, then we can answer the questions about the physical processes involved in galaxy evolution. So here's some specific simulations for Mikado for imaging these galaxies. And just to emphasize again the resolution here, that the resolution we get of sort of 50 to 100 parsecs is equivalent to the resolution you can see now when you look at galaxies in the Virgo cluster, so really local galaxies. And that's the amount of detail we'll be able to see in these galaxies, but at high redshift as well. So it's going to be really remarkable. Mikado is going to have an array of 3x3 detectors, and we've put them all here. And this is a simulation basically done using the Hubble Ultra Deep Field with known sources and some additional structure and extra sources thrown in as well. And on here, it doesn't look very impressive because basically this is 12,000 pixels, and the projection screen would have to be about 10 times the size in each dimension to see it properly. So here's a couple of blown up regions. These bars here are now 0.2 arc seconds, okay, in each one, and you can see an amazing structure on scales of tens of milliarc seconds. This is all structure we've added, but it shows the sort of thing you can do. You can measure the luminosity functions of the star-forming clumps, for example. So it's going to be really remarkable, the sort of detail we're going to be able to see in these very high redshift galaxies. But one thing to bear in mind is that here, this is 10 hours integration on each of 3 bands. So these aren't things you can measure easily. This is a big investment of telescope time to see these sorts of things. And so if you come to what are the requirements for high-resolution imaging to be able to do this sort of science, we need big sky coverage because we're looking in deep fields to get all the ancillary data, but there aren't any good guide stars there for adaptive optics. We need sensitivity because these simulations are already 10 hours, and really you'd like to go deeper still, but you need that in multiple bands, so it's going to take a long, long time. And because you need long integrations, you need to be able to get your performance, your high resolution, even in poor conditions and at high air mass and so on. All those are very difficult to do. So this requires more than just a standard AO system that you find on any telescope now. You need very special and complex types of AO systems. They've been tested many times, but there's very few facility AO systems that do that sort of correction. We need them to work really well in poor conditions. And really what we'd like is simultaneous multiband imaging. So wide format energy resolving detectors, that would be really good for this sort of science. So what about the next case I want to look at, galactic archaeology? Well, we've just been talking about measuring galaxies at high redshift. So if you know this diagram, this is the star formation rate density as a function of look-back time. And you want to look at galaxies basically back here where the peak of the star formation rate was. But instead of looking at these galaxies forming then, what you can do is look at local galaxies and trace the relic stellar populations. So you look at a nearby galaxy, make a color magnitude diagram, and what you find, for example, this is the star-forming branch, this is a red giant branch. This black branch across the middle is a horizontal branch, and this traces the oldest stellar population. So if you can see this branch in your color magnitude diagram, you're tracing these populations up here that formed at or before the peak of the cosmic star formation rate. And this is a very exciting capability to have. And it's one that people try now, and HSD's done fantastic work in the galactic halo galaxies. What we can do with JWST and ELT is push this out to basically the Virgo cluster. And so we can see these spatially resolved stellar populations. With JWST, because of the limited resolution, we'll be working at the edge of these galaxies. With the ELT, because of the high resolution, we can push right to the middle and still separate the stars out to measure the color magnitude diagrams. Just to give you an idea of what this really means, because seeing it is very different to just hearing the words, here's some simulations we've made, and it compares the same stellar field that you can see as you would see it on HST, on JWST, and on the ELT, okay? And this top one is done at a stellar density corresponding to the outer part of a galaxy in the Virgo cluster. And you can see actually HST would struggle here, but JWST already, you can basically resolve the stars. So that's the regime JWST is going to work in. The Mikado field looks empty because the stars are so small, you basically don't see them on the projection. If you push right to the center of this galaxy, that's what this bottom panel shows. Even JWST is basically useless in this region. You can count just a few stars, but if you look at the Mikado field, you realize that even those few things that you think are individual stars are actually multiple stars, and you really need the highest spatial resolutions to do the science and measure the star formation histories in the centers of these galaxies. So that's a very exciting capability. I maybe misled you a bit because I was showing you a color magnitude diagram taken in the optical, but of course, adaptive optics on telescopes, especially big telescopes, works in the near-infrared, and color magnitude diagrams are a bit more compressed in the near-infrared. So that rather nice horizontal branch I showed you is this little sort of bit down here. Admittedly, this is a color magnitude diagram where the horizontal branch isn't pronounced, but you can see that you've got to have very, very precise photometry to be able to measure this in the near-infrared, and it'd be much better to do it in the optical. And that, in fact, is one of the main drivers for developing visible adaptive optics on the VLT. That would going to be very exciting because the resolution you get of about 10 or 50 milliarc seconds matches exactly the resolution you get on the ELT in the near-infrared. And if you could combine the infrared and the optical on the VLT, you could do fantastic stuff with that. But that's a very difficult project. There's an instrument project called MAVIS that's just started its phase A. And sometime in the 2020s, it'll be on Sky on the VLT. And then maybe 20 years after that, as I said, maybe we can do it on the ELT as well. So what do we need to be able to do this sort of science? We need spatial resolution, so telescope diameter is everything. We need a uniform PSF because precise photometry is everything. And if you don't have precise photometry, you can't measure anything. And we need to get to the short wavelength. So you need to push your AO systems to work really well in the visible as well as in the infrared. And all these are big challenges. I mean, particularly, it's something worth thinking about is PSF characterization to do your photometry. Many people who work on photometry on the VLT with adaptive optics really don't like the PSF shape because of the core and the halo. On the ELT, the halo is going to be a factor of 20 or 25 fainter than on the VLT, and so you'll only see the core of the PSF. And maybe that makes it very nice and clean to make your measurements, but also it makes it very hard to do photometry, because unless the adaptive optics system tells you what performance you're getting, you've no idea how to scale your counts you're measuring to a real flux. So it solves one challenge and gives you another one instead. I want to move now to a different regime, the Galactic Center. So this is sort of the archetypal dense stellar system, and here's a fantastic adaptive optics image taken in the near-infrared, HK and L bands, I think, of the Galactic Center. There's many different types of science you can do there. There's strange dynamics in the young stellar population. The old stellar population seems to have a missing cusp that you would expect to be there. We can see flaring from the accretion onto the black hole itself. There's gas streamers that we see, and we don't really know where they're coming from or what happens to them. And there's relativistic effects on the orbits, and it's that last one, the relativistic effects, I want to say a little bit about today. Just as a zoom in, this is about a 1 arc-second circle of the center on the Galactic Center, and this yellow ellipse is the orbit of the S2 star, which goes around the black hole every 16 years or so. And this has been monitored now for about 25 or 26 years. And it's tracking its orbit is almost a history of high-resolution imaging in itself. You can start back in 1992 with speckle imaging on 3.5-meter telescopes. Then they started speckle imaging on 10-meter telescopes. And then the adaptive optics started. And in each phase, the error bars got smaller and smaller. And so now we've measured it on, I think, almost 2 complete orbits it's been measured for. And so we have very, very precise measurements of the black hole mass, of the distance to the galactic center, and so on. You can't just use proper motions for this, of course. You need to have velocities as well so you can fit the orbits in 3D. So we've been monitoring this with Symphony as well to get the velocities. And what we can do recently is we've been applying gravity to the galactic center, and this is an incredible leap in resolution and precision. So I showed you in the previous figure, measurements been taken sort of every month or so. When we pointed gravity, the VLTI interferometer at the galactic center, these measurements are basically taken on different nights. You can measure from one night to the next the motion of the star around the black hole. And at its fastest, it's moving at a sort of 7,500 kilometers per second, which is that's along the line. That's its velocity in 3D space, and it projects here so that you can actually see it moving from night to night. If you do your image reconstruction, this is a sort of image you get, and you see the flares on the black hole, which are basically there continuously when you can get to this sensitivity. To the distance of S2 is you can measure it down to much better than milliarc second, down basically 10, 20, 30 microarc second precision in astrometric separation between these objects. What's remarkable here is the sensitivity. So Sagittarius A star in this image has a magnitude of 16.6 magnitudes in K-band. And the noise in the image means that any star brighter than 19th magnitude in the K-band you'd see, and that is many magnitudes more sensitive than any other interferometer. So it's really remarkable what gravity can do. What it's allowed us to do is pin down the orbit parameters so precisely that when you measure the velocity, you can actually measure very significantly deviations from Newtonian orbits. And this basically grey line here shows you what the best fitting Newtonian orbit would be given all the data. You can see that deviations from this are around 200 kilometers per second. And this is a gravitational redshift and a transverse Doppler effect here contributing to this. So this is in a first time measured around a massive black hole, the relativistic effects. So what do we need to do high-resolution imaging for dense stellar systems? And here I've included all dense stellar systems, not just the Galactic Center. We need spatial resolution again, because we need to measure individual stars in crowded fields. And we need very precise astrometry. And that's really important, because we need the proper motions of the stars in order to measure the anisotropy and get a proper estimate of the mass, not just the black hole mass, but the extended mass, which might be an extended stellar mass or a dark matter mass. And this precise astrometry is extremely difficult to do. It has implications on everything in your instrument design and usage. And I wasn't sure where to start, what to write down, so I just picked a couple of things here, and controlling and calibrating distortions. And these distortions aren't just in the instrument, it's how the atmosphere and the telescope and the AO system and the instrument work together. And PSF characterization is very important as well. And in a way, maybe it's a question of whether you have to reconstruct the PSF using your AO data, or whether you can empirically derive it from your data. Neither of these is optimal, and maybe one has to use a bit of both. And the only saving grace is the fact that on small scales, the PSF shouldn't vary very much within a small region. And on larger scales, we know it does vary, but maybe larger scales is not so important as what's happening on small scales. So the last thing I want to talk about is high contrast imaging. And here I want to compare what you can do with the JWST and what you can do with the VLT. So on the left is the JWST, and JWST's strengths are sensitivity and low background noise. And this means it's going to be really good for working around faint primary stars. Its problem, of course, is that it's got a very segmented mirror, and by the time you've put a Leo stop after your coronagraph and masked out also the segment edges, your pupil, which is what's left in white here, is a very, very funny shape. And this means your PSF without a coronagraph is horrible. Even with a coronagraph, it's pretty horrible. And that limits how faint you can see planets around bright stars. So the strength for JWST is to see planets around faint stars. And that we can't do from the ground, because from the ground you need adaptive optics, which requires a bright star. And so the very complementary things, we're going to be much better from the ground at small separations, less than an arc second or so. This is a simulation, but basically it's showing that in an hour at about 3 or 4 microns, you can get above a signal-to-noise ratio of 5 at a contrast of 12 magnitudes at just 0.3 arc seconds away from the star, and that's pretty good. So if that's what we can do on the VLT, which is already pretty good, what can we do on the ELT? Well, we can do much better, of course. And we can do much better because we've got a bigger telescope, and so we can get to a smaller working angle, and we can measure exoplanets or anything else much closer in to the primary star. And so the key science cases, at least for Mikado, not for the ultimate planetary camera system, but for the first light cameras, would be looking at exoplanets at small orbital separations. And what's really remarkable to think is that even with a simple imaging camera on the big telescope, we're going to do better than Symphony, which is a sort of optimized, not Symphony, sorry, Sphere, which is an optimized exoplanet camera on the VLT. And the reason is we can go to smaller radii because the telescope's bigger and the PSF is then narrower. And we gain in the speckle noise as well, simply, again, for exactly the same reason, that the contrast between your core of your PSF and all the speckles is much, much higher. So we gain in both regimes. And just to give you an idea of what we'll be able to see, here's some real data of 4 planets around HR 8799. This is a well-known system, and there's nice movies of these planets going around. This is a real image after 2 hours of integration on Sphere. This is a 30-second exposure with Mikado, okay? All these are AO effects. But in fact, already in this single exposure, you can see 2 of these planets here and here without any post-processing at all. If you do your post-processing, then after about, I can't remember how much integration this is, it's not so much, these planets become so bright that you can even see airy rings around them. And then if you put artificial planets closer in, say this one here and here, you can get an idea of how much more sensitive you'll be simply because you've got a bigger telescope with adaptive optics. And in fact, what's very exciting here is these are almost the planets that Gaia will be sensitive to, so you can get dynamical masses as well as photometry directly, and it's going to be very, very exciting. So what do we need to do this? We need to focus on the highest AO performance, but not just for the brightest stars. We need to push this to the faintest stars we can manage. We need to suppress the speckle halo as much as can, and this affects the choice of AO system because pyramids, you get a much more stable, much better suppression of the halo because it's got better control of the low frequencies. And we need novel coronagraphic mask designs to do the best nulling of the central star, maybe give us the best references for photometry and astrometry and so on. So for me, at least, the technical challenge here is achieving the small wavefront error budget, and this affects everything in the instrument. It's extremely difficult in the adaptive optics side for the wavefront sensing and the deformable mirror for the correction. You've got to have really good wavefront control, not just with the AO system, but afterwards for your non-common path errors and for your optics and thermal distortions and so on. You need to have good diffraction control, which means your phase mask for nulling the central star so you can see well around it. And you've got to have data processing. If any of these steps fail, then you can't reach the contrast you want. So all of these things are particularly challenging for this science case. So I just want to finish by saying adaptive optics is basically inevitable if you want to get to high resolutions from the ground. And basic adaptive optics is mature, and it'll give us 50 milliarc seconds, but there's a lot of more complex AO options around that have been tested and known to work, but I would consider them at the moment to be pathfinders rather than facility-style systems. And while we can get, and I think extending this to adaptive optics on large telescopes and visible adaptive optics on the current generation telescopes, these are both very challenging things. Interferometry is also a fantastic thing for high resolution, but it's typically limited to very bright sources. And I think the second generation VLTI instruments are going to change this, and I think it's going to be very exciting in the next 5 or 10 years what they can produce and what sort of targets they can look at. But these sorts of projects, they're big projects, they're long-term projects, and they're very expensive projects. And I think it's very important that we keep open the idea of having novel techniques which we can apply in niche regimes and get happening on faster timescales. Thanks very much.
Do we have any questions? Yeah, because we're being recorded, please use the microphone for questions.
You said that the ELT can direct image small separation exoplanets a few AU from up to 20 parsecs away. So to put that in perspective, if the ELT was 20 parsecs away and looked back at us, how much of our solar system could it image?
It wouldn't image the Earth. It would easily get Jupiter and Saturn. I'm not sure which other planets it would get.
Rick, you made a fantastic case for the superb imaging with ELT for stellar populations, and also you stressed the need for very long, getting long integrations on this. But you then went on to say something which puzzled me. You said the technical challenge of working at high air mass, and if you're using ELT, surely you should always be using it at its optimum efficiency. You don't need time resolution, so you just get your exposure over several nights. I can't imagine people accepting that you would be pointing the ELT at high air mass.
In an ideal situation, I would agree with what you say, but if you look at what's actually done on the VLT, that's not how things work. You very often have to work at higher air mass, and by higher air mass I mean more than 1.5, between 1.5 and 2. And it depends on what field you want to look at. Unfortunately, many of the deep fields for extragalactic objects are in the northern hemisphere. I mean, okay, we have southern ones as well, but you also want to look at the northern hemisphere ones, and then you're pushed to high air mass just by where the objects are. Not everything's very conveniently transiting over where the telescope's going to be. If it is, ideal, but not always.
Questions? Thank you again.